Welcome to this lecture. This lecture is basically the first lecture of a new module, and in this module we are dealing with some multiple random variables. So you know that so far as whatever the lecture we have covered the single random variable. We have covered their different properties of the probability distribution, and we have discussed some standard distribution that is available and their properties as well. So this module onwards, we are starting that multiple random variable. This multiple random variable, as its name states, that there are more than one random variable is there. So in many cases where we are dealing with two random variables, it is known as bivariate random variable, and if it is more than two, then generally we call it as a multivariate random variable. So this entire module we will discuss about about different properties of more than one random variable, particularly in cases when we deal with that different modules, the different random variables which are associated to each other. This is important in many application field, including civil engineering, and we will see that in many cases that for the single random experiment, it is possible that there are more than one random variable are associated to each other. So when we are saying that these are associated to each other, that means that their behavior are somehow related to each other, somehow associated to each other. So we have to study all the random variable associated to each other jointly. So now when we are talking about that this joint behavior of this random variable, that time this multiple random variable, the properties and their analysis and all these related issues comes into picture, and that is our focus throughout this entire module. So in this very first lecture, what we will discuss about there, first we will start with that joint probability distribution. That joint probability distribution, here what we mean is that if one random variable is associated to one random variable, that is one particular outcome is associated to the other one, then how means how their behavior we can study jointly with the behavior of the adjoining random variable or the associated random variable here. So here also that line of discussion will maintain the same or in the similar path that we discussed for this single random variable. That first of all we will discuss about its definition, how it is different, or how it can be related to that concept of this random variable. We have discussed the concept of the random variable for a single random variable earlier. Now we will see that how the same concept or how the concept differs when we are talking about more than one random variable. That concept we will discuss first, then we will discuss about its definition, and first significant thing that we will see is that how the probability is distributed. Because when we discuss about that it's single random variable, then we have told that we have seen that over the entire range of this random variable how the probability is distributed. Now in this case what will start that if there are more than one, then how the distribution will look like and how will be their properties. So this will take up in today's lecture. So the outline of today's lecture is that first we will discuss about this this multiple random variable, and as I have told that if there are two random variables, which is very common, and many cases we generally deal with these two random variables. So that is that specially we know these two random variable as this bivariate random variable. This bi means you know that there are two random variables are associated, and sometimes that more than two we call that multivariate random variables. So multiple random variables, this is multivariate analysis, it will go under that. So after this concept we will discuss about their joint probability distribution, and this joint probability distribution again similar to the single random variable. Here also there can be two possibilities. One is that discrete random variable, and you know, for a single random variable, this discrete random variable, when we are talking about the discrete case, that time what we did is that some specific value over the range, only some specific value is possible for that random variable can take. So here also means when we are talking about two or more, so a specific combination of three or two random variable outcome is possible, not the entire range. So that time we will be this will be considered as a discrete random variable. So far as the concentration of the mass, this mass means the mass of this probability. You know that for the discrete random variable we call it as a probability mass function. So here also those mass will be concentrated at some particular point in case of this discrete random variable, discrete multiple random variable as well. So so this is for the discrete, and then from this mass function we will also discuss the concept of the cumulative distribution function, how we can integrate that mass function to get that joint cumulative distribution function. And these two things, you know, for the continuous random variable we generally call it as joint probability density function, that is joint PDF, and similarly that joint CDF, cumulative distribution function. Basically here the concept is important in the when we are talking about more than one, that time the concept in the sense that when we are doing some integration or when we are referring to some particular value of the probability, then what should be the related graphical representation, that is important. And you know, for the graphical representation we can only define, we can only show only up to the two random variables. So that if the concept is clear for the two random variables, that is bivariate case, then the similar concept can be extended to the more than two random variables as well. So that concept will basically, or the pictorially we will try to understand for the bivariate case first. So as I told that so far we have gone through the various concept of theory of single random variable, and in many cases we will be dealing with more than one random variable within the same experiment and the same sample space. So if I before I go to the civil engineering problem, if I want to give an example of the throwing of a dice, then what I can say is that instead of taking one dice, I can take two dice and throw them simultaneously, and I can observe the what is the outcome of each dice. So for a single random experiment there are two possible outcome is there, or that if I take the two coins and toss them together, then the outcome is a bivariate random variable. So I can relate that outcome to a bivariate random variable, because you know that this outcome of a random experiment is related to the real line, some outcome on the real line through a functional relationship, and that function indeed is the random variable. So the traditional examples are this. So the experiment is such that there are two outcome, or the more than one outcome is feasible in that experiment. So those outcome is generally considered in case of this multiple random variable. So similarly, that to handle this situation means where there are more than two possible outcome is there. So we will extend the theory from the single random variable to two random variable first, this bivariate case. As I told that this is the pictorial representation is possible only up to two random variables, and then the same concept in a similar way can be extended to the multiple random variables as well. So now if we recall from our earlier lecture that the random variable is a function that map each points over a sample space. Each points here we mean is that each outcome of one random experiment to a numerical value on the real line, and this function means this functional correspondence between this outcome to this real line value is your random variable what we have seen. Now in case of, if we consider the two or even more random variables, that means two or more outcome we are dealing with together, then both or all of them, if it is more than two, then both of them mapping from the same sample space, from the sample space to that real line, to some numbers. So accordingly, then the definition of multiple random variable can be stated as an n-dimensional random vector, that is the vector of random variables is a function from the sample space S into Rn, where this Rn is denoting that n-dimensional Euclidean space. Now as I told that it will be easier for us to first conceptualize it in case of the two-dimensional case. So here if we just want to say that bivariate case first, then it is a two-dimensional random vector having two random variables in it. This is a function from the sample space S into a two-dimensional Euclidean space. So here I will show that it's how the pictorially it looks like in a minute. So what is meant here is this n-dimensional Euclidean space is that for any non-negative integer n, the space of all n tuples of the real number forms an n-dimensional vector space over R and denoted as Rn, where this R denotes the field of the real numbers. So what we are just, if we look at here on this, that means what we are basically looking for is some two axes we are just looking for. So earlier this was the axis that we considered here, that is the for a single random variable x, and we have observed that how the probability is distributed over this. Now what we are doing here, or what we are trying to explain here, is that there are more than one random variables, and for the pictorial representation we are considering only two random variables. So there is another axis where the other random variable which is associated is represented. Say that random variable is y. Now so this is the, this is your that surface or the plane over which I am, so some area is your feasible space, and over this I will describe how this probability is explained. So this is the axis of this, either whether it is a that PDF or PMF, or this can be even the cumulative distribution function. So now the possible, suppose the possible range of x is from here to is here, so you know that this is called the support of the random variable, and say that this is the range for this y, or the support of this y. Then basically this joint distribution is defined over this area. So this is the area. Now what we are talking about is that, so this is the area where that probability is distributed. So in case of the single random variable, we have seen that the probability distribution what we are considering over a line, over one axis, and here in case of the bivariate case, this is over a two-dimensional space. So over this space, how this probability is there, so that distribution will now look like a surface over this area. So this is what, and similarly what you can do is you can extend this idea to the three-dimensional or even that more than three random variables case. So those are accordingly that over which the probability is explained, that is defined. So now so here we just used one word, the n tuples. So in case of the bivariate case, there are only two only two possible things are 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 associated, because this one that 2 points will that x equals to some value and y equals to some value will refer to one point here. Now if this is for the three random variables together, then there will be three such value, and this will refer to a point over a space in this area, and in that point how much what is the probability, how the probability is distributed, that can be analyzed. So this is what is meant here in case of this n-dimensional random vector, and this n-dimensional Euclidean space is referred to. Now here, as I was just showing here in this case, is that this graphical representation, as I told that this is for the bivariate random variables case, requires a three-dimensional form in which the two horizontal axes represent the two random variables and the PMF or PDF is measured vertically. So here you can see that, so this is my sample, sample space of this, which consists of this all possible outcome of this of one random experiment. Now each outcome of the random experiment now there is that random variable, that is the y is the random variable, which is a function which is taking that outcome to a point over the over some point over the range of this y. Similarly, the same outcome is also referring to another point over the random variable x. Now this combination, for this bivariate case, there are only two values, the x and y. So this x and y refers to a point over this xy plane. Now at this point, now if we have, the way it is shown is that it is a PMF, that is probability mass function. So at this point, how much probability is concentrated in this point? So that is what is explained is as the probability mass for the outcome, for the specific outcome here it is shown for the random experiment. So for this outcome, the probability that is concentrated is here. So there are such, so over this entire space there may be many such outcome, and each outcome will correspond to 2 points, one is on the x and another is on the y, and that will correspond to a point over this plane, and that will have some different probability. So instead of distributed over a line for a single random variable, this is now distributed over a surface, again when we are calling that surface, that means I am referring to the bivariate case. So over a surface, how it is distributed, that is the PDF or PMF for a bivariate case. Now the multiple random variables, as I told that there are that these two random variables is given a special is specially categorized as a bivariate random variable, and more than that is all are multivariate random variables. So for simplicity, first we shall consider the two random variables, that is a bivariate random variable, that is when we take that n is equals to 2, so that our random vector becomes an ordered pair of this x y, that what we discussed through that pictorial representation. Now when we are talking about this, again this bivariate random variable, when we are taking it, now this also will discuss in case of two different cases, that is the discrete case and the continuous case. You know, the discrete case, it can take only the specific values, and the continuous case, it can take any value over the entire support of the random variable. Now this many of the interesting situation in the field of civil engineering can be dealt with two random variables. So these are the bivariate random variable case. So an example we can talk about that average rainfall over a catchment area and the volume of the stream flow passing through the outlet of the catchment over a period of time. So now this rainfall, what is the rainfall that has occurred over a catchment, and if I take that what is the stream flow for that time that has passed through the outlet. So these two can can have some association to each other, and these two can be, if we want to analyze these two simultaneously, then we can even we will get a bivariate random variable case. But here one thing is very important that we should mention here, because this should not create the confusion, that whenever we are taking more than one random variable, it is not necessary that they will always be associated to each other. That means what I want to mean here is that that the random variable that we are consider can eventually be independent as well. So it is not that always means association doesn't mean that always there should be some kind of relationship or some kind of mathematical relationship should exist. These two random variables can even be independent to each other. So the association, when we are referring to the word association, that independent is also one type of association between the random variables. Coming to the civil engineering problem, that the first example that we have discussed is that is the rainfall and the stream flow from a catchment, and second and we can even think of the other examples. For example, the traffic volume and the average speed of the road. So average speed at a particular section of the highway, if we see that what is the average speed that the vehicle can pass through, and what is the traffic volume to that. So this will also is a bivariate bivariate random variable case. So in such a way, there could be found there could be many such application can be found out for these different civil engineering problems, and here we'll discuss about some problems in this lecture as well. And before that, some of the properties of this joint probability distribution and their some more that how it can be conceptualized both in case of the discrete as well as in case of the continuous random variable, that we will see first. So the example that we are talking about is the rainfall over the catchment area and the volume of the stream flow that is passing through the outlet of the catchment. This is there are two random variables, so this is a bivariate random bivariate case. And if also in this two, if we are also see the take the groundwater table, such as the depth of the groundwater table also, if we consider along with these two random variables, then it becomes the multivariate case. So all three random variables can be analyzed together. Now when the probability distribution function, when we are talking about, you know that this is also referred to as a cumulative distribution function. That is, what is the probability when particularly in case of the single random variable, you know that when we are talking about that time that this probability distribution function or the cumulative distribution function, when we are talking about, that means the how much probability is there for the random variable less than equal to a specific value. So that we refer to as this cumulative distribution function or probability distribution function for that point. So for that point, so when we are talking about that fx of x, that means that random variable x is less than equals to that specific value x. Now when we are talking about this multivariate case, especially here that bivariate case, so this has to be referred to as that both the random variables will be less than some specific values. So the occurrence of both the events should be simultaneous. Means what I am talking about is that if you just see it here, that suppose that this is the specific value of the x that I am talking about, is the x, and if there are some value here that we are talking about is that y, then that for the single random variable from the left extreme of the support to this specific point we have integrated. Now when we are talking about the bivariate case, that means both the cases, that this is suppose the specific value y and this is suppose the specific value x, that I have shown it here. So now both the cases, so that x should be less than equals to x and then this y should be less than equals to y. So this area if we take, so this area if we take, if we just integrate what is the total probability in this area, that will give you that the probability distribution up to the point x comma y. So what I want to trace here is that occurrence of both the events is important. It is not that either of these two, it is that this and this, or this as well as this, when both the things are satisfied, then is that that is the basis of that defining that cumulative distribution function or the probability distribution function. So now here if you see that the probability of two event A equals to x less than x and B equals to y less than y, defined as a function of the x and y respectively, and is called the cumulative distribution function CDF, cumulative distribution function CDF. Now this is for the single random variable if we consider them separately. Now to consider the joint event, when we are talking about the joint probability distribution, then this x less than equals to x and y less than equals to y, this concept is called the joint distribution function. So how this is done is this one, that if x and y are two random variables, the joint probability distribution of x and y is a description of the set of points x, y in the range of the random variables x and y along with the probability of each point. The joint cumulative distribution distribution function of x and y is denoted by that f, this capital F x comma y for some specific value x y is given by that this this probability distribution is equals to the probability of that x less than equals to the specific value x intersection y less than equals to the specific value y. So here you refer to that the intersection when we are talking about, that is the joint occurrence of both the events is required. So when these two events are occurring jointly, that probability is equals to the probability that the probability at the point x, y. Now the pair that x, y is referred to as the bivariate random variable. Joint probability distribution is also referred to that bivariate probability distribution or bivariate distribution for the case of these two random variables, and generalized to any number of random variables as the multiple as the multivariate distribution. Now when we are talking, so from this bivariate distribution, that what we have discussed now, if we just want to, if we have that more than two random variables, then we can say that, so the simultaneous, suppose that there are suppose that there are three random variables x, y and z. So that f, that is the cumulative distribution of this x, y, z of that some specific value of these random variables which are lowercase letter x, y, z should be equals to the probability of that x less than equals to x, this is one event, intersection with that y less than equals to that specific value, intersection with z less than equals to that specific value of that z. So these three simultaneous occurrence of this one, that probability is your that probability the distribution or the cumulative distribution function at that particular point x, y, z. So here 3 points are three values are considered, which is referring to a single point in a three-dimensional space, extending this to that from the two-dimensional surface to the three-dimensional space that we are referring to. Now this function when we are talking about, then this function should have some properties to satisfy as we have also seen in case of the single random variable. Now these distribution are limited in the lower value and the upper value, similar to the single random variable. Its lower limit is 0 and upper limit is 1, and this x and y can take any possible values of this minus infinity to plus infinity. So in this, so this is these specific values are over the entire range of this real axis. So this can take these values. Now this f x and y is a non-negative and non-decreasing function. This non-decreasing function of this x and y is important, because so that if we get some two values, that is x1 x2 and y1 y2, and if this x2 and x2 is greater than x1 and y2 is greater than y1, then this value, so this f value at x2 y2 should be greater than that x1 y1 for any specific for in any cases over this entire range. So that is what is meant by that non-decreasing function. You can recall from the description of the single random variable that the PDF, that is that CDF, that is cumulative distribution function, is also starting from 0 and going to 1, and that is also a non-decreasing function, because you know that this function actually is obtained by the integration of the PDF, that is probability density function, and when we are integrating it from this left extreme and gradually going towards the right extreme, that means at each, for any small step over this over the range of this random variable, we are adding up gradually to the previous value. So obviously this will be a non-decreasing function. Now at the infinity, when both are on the right extreme, this x and y, so this should be equals to 1, and when it is on the left extreme, this will be equals to 0. When either of them to the left extreme, so this function should be equals to 0, whether x is on the minus infinity or the y is on the minus infinity, these values are 0. And when either of these on the right extreme, then it gives a new distribution which is f y y, and when that y is equals to that infinity, so this should not be minus infinity, this will be plus in infinity. So when the y is the plus infinity, then this function reduces to the fx of x. Now these two again will take up these two in detail in the next lecture, which is known as the marginal distribution. So irrespective of the distribution of one random variable, if we consider what is the distribution of the remaining random variable, irrespective of the distribution of the other one, then what the distribution we get for the one random variable, that is the marginal distribution that we call, and this we will take in detail in the next lecture. Now joint probability distribution of the discrete random variable. So the discussion that we have done is basically for the general case of this random variable. Now if we are talking about the discrete and continuous, there will be a little difference, as you know that the discrete can take only the some specific values over the range, and the continuous random variable can take the any possible value over the range can be taken. So for the discrete case, if that the r square is the subset over that plane, that xy plane, then it will be a discrete random. If it is a discrete random variable, then you know that we generally call it as a mass function. So here it is joint probability mass function, or joint PMF. The joint probability mass function of two discrete random variable x, y describe how much probability mass is concentrated on each possible pair of x, y. So there are some possible pairs are only possible, so at that point it is not the density as against to the continuous random variable, this is the probability mass that is concentrated, as we have discussed earlier in that pictorial view, that is at that point some probability mass is concentrated at that point. So the joint PMF is given by the intersection probability, that is Pxx. You know that when we are talking about this mass function, our notation is the small p. between that bivariate case. So this is the bivariate random variables are x, y, and when we are talking that some specific value, that is x and y, is equals to that probability x equals to that specific value and y equals to that specific value y, and there when both the things are occurring simultaneously. So this one and this x and y can is from the sample space S. Now, when for this discrete case, when we are considering that cumulative distribution function, that this cumulative distribution function now is the summation of that all such xi yi, where this xi is less than equals to some specific value x and yi is less than equals to some specific value y. So what we are, so if you again refer to this figure, suppose that in this zone, now if this is, now if I just redraw the same figure here in case of, because this is the discrete case. Now in this suppose this is the possible entire zone and there are some specific values are possible. So at each point some probability mass is concentrated here. Now if we are taking some particular value of this x and some particular value of this y, then this is the x and this is y, and this the cumulative distribution function that we are adding up means less than this and less than this. So these three probability mass should be added up to get the cumulative distribution for this up to this range, that is from the x and y. This is what is explained, and as these are the discrete case, we are just adding them up through summations, which is the sum of probabilities associated with all pairs xi yj in the subset of this case, that is xi less than x and yj less than y. Now these properties of joint PMF, again this PMF, this value this value, that is PMF, what we are talking about, this can have a lower limit 0 and upper limit 1. If we just add up these probabilities, then this will be having this should be equals to 1, and if we just add up to some specific value of this x and y of this function, then it will be that the cumulative distribution function, which is denoted as a capital F x y x comma y. So using those properties, here we can quickly see one problem, that joint PMF of two random variable x and y is given by this equation, that is pxy is equals to k multiplied by 2x plus 5y, where this x is equals to 1 comma 2 and y is equals to 1 comma 2. So that means that x, y can take the values only 1 and 2. So here you can say that the joint random variable, that is the bivariate random variable x, y, can have a 4 possible outcome. So those 4 possible outcomes are what? These are 1 1, 1 2, 2 1 and 2 2. So these 4 cases it can take, and otherwise it is this value of this probability mass function is 0 for all other cases. Now the question is, what is the value of k? So we have to find out this the value of the k to be a because it has to satisfy the properties that a PMF can take. So here you know the properties are that if we add up this probability mass function over the entire range, then it should be equals to 1. So using this property, if we just add them, that is x can take the value x equals to 1 to 2 and y can take the value 1 to 2. So if we just take this function and put their values, then we will get this expression, putting that the first one is the x equals to 1 and y equals to 1, second one is x equals to 1 and y equals to 2, and similarly it is going on for these 4 different cases, as I told that which are the 4 possible outcome that can take. So all these 4 possible cases is taken, and it has been found that 42k, and you know that this 42k should be equals to 1. So from this one we can say that this k equals to 1 by 42 to this be a valid PMF. So this value of k we got it from using this property of this of this PMF. So this kind of problem we have seen earlier in case of the single random variable as well, where we are just considering only one output or only one possible value of a single random variable, and here you have seen that when it is coming that multiple random variable, here it is bivariate case, so two random variables are there. So both the outcomes we have considered in this in the properties of this PMF. Now if we take another problem on this the stream flow categories, sometimes what happens, just to give a little background, is that sometimes we are interested to know the behavior of the stream flow of a new river stretch where there might be that data was not that reliable, but the adjoining data from a adjoining river gauging site is available to us. So we just want to know that what is the that probabilistic relationship, how their bivariate relationship between the stream flows between two sites. So if the sites are nearby, then we can assume that they are we can analyze some sort of probabilistic dependence to each other. So to do that, here we have considered the case, because the stream flow, you know that it is generally considered to be a continuous random variable, but in many cases, for example, that when we are talking about some, you will know that the Markov case. So there we generally categorize the stream flow into different categories, and those categories are now important. So this categorization means that if the stream flow is below a specific value, then we categorize as 1, then if it is between this range to this range, then we categorize as 2. So this is the way we can categorize the stream flow before the analysis. So once we are categorizing the stream flow in this way, basically this is become a discrete random variable. So here such example is taken here, that the stream flow at two gauging stations on two nearby tributaries are categorized into 4 different states, that is 1, 2, 3, 4 for the both the cases, both the tributaries. So these categories are represented by two random variables x and y respectively for two tributaries. The PMF of the stream flow categories x and y are shown in the table on the next slide. Calculate the probability of x greater than y. So the PMF of the stream flow, before I go to the next slide, that PMF of the stream flow categories x and y are shown on the table on the next slide. So what we are expecting in that PMF that is supplied to us, and we have already told that there are 4 such categories, is that 1, 2, 3, 4. So PMF means the how much probability mass is concentrated for each possible outcome. So x equals to 1, y equals to 1, this is one possible case. So what is the probability mass is concentrated at this point? Now again, so 4 by 4, so total 16 such combination is possible. So for all these 16 such possible combination, what is the probability mass that is concentrated at each possible outcome? So that is what is represented through this PMF. Now once we know this PMF, then we are interested to know that what is the probability that x is greater than y. X is greater than y means the first tributary is having the higher category of stream flow compared to the second tributary. So if we want to know this probability, then we have to pick up those combinations where the x is greater than y. So such combinations means what? We have to take the first possible case is 2, 1, x equals to 2, y equals to 1. Secondly, that x equals to 3, y equals to 2, x equals to 3, y equals to 1, both the cases when x is taking 3. Similarly, when x is taking 4, then y can take 1, 2, 3. So all such cases, whatever the probability is there, if we add up, then we will get the required probability which is asked for. So first of all, we will see the PMF here. you can see that PMF when x equals to 1, y equals to 1, this is 0.31, this x equals to 1, y equals to 2, then it is 0.06. And here one thing you can observe, that as these streams are adjoining, means nearby to each other, so it is highly possible that both the states should be equal, and that is here reflected through this heavy diagonal. You see, these diagonal terms are generally more than their adjoining terms. So that is why what you can say, that both the streams are having the tendency to be in the same categories, and also both the streams, when it is 4 and 4, there is very less probability, in the sense that both the streams doesn't go to the very extreme rainfall, so that probability is less. Now, to solve the problem, only this 4 by 4 matrix is sufficient for us. Now, there is one more additional information is given here, which is here this pxx and which is here the pyy. These are nothing but the summation of this individual rows, and these are the summation of this individual columns. So this is basically, basically what you can say, that irrespective of whatever the distribution of one random variable, so if we are considering this one, that is y is equals to 1, when we are talking about the y is equals to 1, we are considering the irrespective of this value of this x. This is what we are just a few minutes back was discussing about the marginal probability distribution, and this will be taken in the next lecture to discuss that what is the marginal probability distribution. But here what this last column, I have just included it intentionally just to tell you the concept that this can be added to get that the what is the probability concentrated is x equals to 1 in this case, irrespective of whatever may be the value of y. This will take up later. Now, as a quick check, what we can do is that this 4 by 4 matrix that you can see for these different possible values of this x and y, if we just add up, then we should get this summation should be equals to 1. If we get this summation equals to 1, then only it will be a valid PDF. Because we have already told that these are the 4 possible cases, that there are 4 possible states that it can take. So this is beyond this there is no such possible outcome is expected, is possible. So that is why the summation of this itself, the probability should be equals to 1. That is what is shown here. Now, as we are discussing that, we are supposed to get what is the probability of x greater than y. So we have to pick up those combinations. So for example, x equals to 2, y equals to 1. So this you have to pick up. Similarly, x equals to 3, y equals to 1, x equals to 3, y equals to 2, x equals to 4, y equals to 1, x equals to 4, y equals to 2, and x equals to 4, y equals to 3. We are not supposed to take even that x equals to 4 and y equals to 4, because in the problem it is asked that x is greater than y. If it is shown that x greater than equal to y, then we have to take even that equal parts as well, that x equals to 1, y equals to 1, x equals to 2, y equals to 2. We will not take, because we are asked for only that x greater than y. If this is understood, then these are straightforward, that this is the event which is the represented by the set 2 1 3 2 3 1 4 3 4 2 and 4 1. So this all these sets are there where this event, this condition is satisfied, x greater than y. So we have to just add up these probabilities to get that one. So so we are just taking this this summation to do this one, and all these probabilities are added up, and these probabilities are picked up from that table, and we got that 0.096 is the probability for the event x greater than y. Now, if we take that concept to this continuous random variable, you know that for the continuous random variable, as it can take any possible value over the entire range, so that instead of the summation we have to go for the integration, we have to integrate it. Now, for the bivariate case, we have to integrate it over the entire area, and if it is the more than 2, if it is 3-dimensional, then we have to integrate it for the entire volume or the 3-dimensional space, and similarly for the higher dimensional space. So here we are discussing this bivariate one. So so it is analogous to this bivariate PMF, where we have just used a simple summation. So if this xy be the continuous random variable, then probability is defined by the integration of the joint PDF over the region of interest. So that this probability of this x1 to x2 and y1 to y2, when these two cases are occurring simultaneously, that means we are referring to that specific area where this x is between these two range and y is between these two range. Now to get this one, we have to integrate the function from this y1 to y2 and x1 to x2. Now this fx and fyy is gives you that what is this probability density function. Now if I just want to show this one as a graphically, if I want to see, now this you can refer as we are just so far discussing that this is a bivariate case, and sorry, this is the continuous case, and in this continuous case it is not, the probability is not concentrated to a specific point, so it can be of entire thing. So entire range, so entire range when it is distributed, that means this is like a surface now. So this fxy is now a surface which is shown here, and what we are referring of this earlier case, that is, so that from the x1 to x1 some specific range we are just talking about y1 to y2. So if we just extend this line, this will consider one rectangle over this, and that over that if we just take that entire volume of this one, so that area or the volume below this curve. Earlier for the single random variable we are talking that area below the curve, now we are talking about that volume below the surface. So if this is the case, then we will get what is that joint cumulative distribution, that probability which is there for the event that x in between x1 x2 and y in between y1 and y2. Now this properties of this joint PMF is that this fx xy should be greater than equals to 0, so this is non-negative, and if we integrate for this entire range of x and y, this should be equals to 1. This is straightforward, taken from what was the properties, that is total area. Earlier we called the below the curve for the single random variable, here the below the surface total volume should be equals to 1 in case of the bivariate. This joint cumulative distribution function, now you know that this is equals to that what's the probability we have discussing. So from the left extreme to some specific value, if we integrate these values, then what we will get is this joint cumulative distribution function. And this joint cumulative distribution function in case of the bivariate one, it will look like this. So we are just adding up the values. So if we just add up these values, this will go on adding to it, and for this each and every value when we are adding, so it will be this surface will be non decreasing in case of the combination x1 y1 and x2 y2, as I just told few minutes back, that if the x2 is greater than x1 and y2 is greater than y1, then the cumulative distribution function will be more at x2 y2 than x1 y1, which is reflected from this surface. And you know that entire integration is equals to 1, that means this will be go and this will end up at when this fxy is equals to 1. So this will start from 0 and it will end up at 1. This joint PDF and CDF, now it is clear that how it is related to each other is that fx x, that is the joint PDF, is the double differentiation of this CDF with respect to both x and y. So if we do this differentiation of this CDF, we will get that joint PDF. So these are the relation between this PDF and CDF, similar to the single random variable, where we have taken that only a single differentiation with respect to that particular random variable. Now, there is a problem on this joint PDF again for this continuous case, but we will take this problem in our next lecture. So, what we have seen today's lecture is the concept of the multiple random variable from the single random variable, how we can extend our concept to this multiple random variable. We have shown some of the graphical representation, how these things looks like in case of the bivariate case, because in the bivariate case the two orthogonal axis is referring to two random variables, and the z axis is showing its probability density or the cumulative distribution. So, these things we have discussed, and we have seen some problem on the discrete joint probability mass function as well, and we will see some example on this joint probability density function in case of the continuous random variable in the next lecture, and also we will start that marginal distribution function in case of the multivariate random variable. Thank you.